Good morning, friends. If I recapitulate whatever we are discussing, our primary focus is on understanding dynamic stability of an aircraft. And how did we start? We said when I try to understand dynamic stability of an aircraft, we need to first identify the equilibrium about which we will be introducing small perturbation. And then we will write equations of motion using that perturbed variable. And then we will find the characteristic equation, and typically we have taken second order system, and we try to interpret this transient response or free response through dynamic variables edit. We want to understand the dynamics of mass spring damper system through damping ratio and natural frequency. So if I write down what we did, number one, we identify the equilibrium. Then introduce perturbation. Of course, small perturbation. Before we introduce small perturbation, you should also notice that we have also developed equation of motion using Newton's laws of motion. These are the primary steps. If I try to recall, see, this is the spring, this is the mass, and here there is a damper. Then we identify first, this is the equilibrium. That is, net force acting on this mass is 0. Now we introduced small perturbation, and this x or x of t, which is measured from the equilibrium. Since it's a one-dimensional motion, so there is a only x-axis we are talking about, and this x is the perturbed motion variable. Please understand, because of this disturbance, the x has been created. And then we release it, and we try to see what is happening to this x. Also, once I draw mass spring damper system, there are salient points to be noticed. One is there is a restoring force, which is typically kx, that is, x is the perturbed variable, and also there is a damping force, which is c x dot, that is proportional to the rate of change of perturbed quantity x. And of course, you could understand that we have assumed linear damping, right? In practice, there could be huge nonlinear damping, but here, since we are giving small perturbation, and for most of the cases, this approximation is not very far off. So these two things should be in your mind when you are talking about mass spring damper system. When you try to model aircraft motion, pitching motion, one-dimensional pitching motion, that is, only pitching is allowed. Here also, we have noticed that we are considering a statically stable configuration. Why I am stressing this? Because here, in this case, it was a linear motion, in this case, the angular motion. And here, the moment I say statically stable means the restoring moment instead of force was also proportional to alpha, and we say Cm alpha into alpha, and of course, Cm alpha is negative. So that is why it is restoring. So similar to Kx, this one, restoring force. And second thing, you also talk about damping or pitch damping. And in non-dimensional form, the pitch damping we model through Cmq into Q, and notice that Q is the rate, d theta by dt, rate at which the attitude is changing, and Cmq is also negative, it is a damping derivative. So this is like the Cx dot. Okay? But here, please understand, C is not negative. Okay? Right? But here, Cmq is negative, so that your net moment is modeled because of damping. It's modeled as Cmq into Q into half rho v square Sc bar. Of course, this is Qc by 2v. So this is the net moment, and Cmq is negative. So for a positive Q, there is a negative moment. So again, restoring. For mass spring system, remember, we model it like this. This is Kx, and we put a minus sign here, and this is Cx dot. But this is again the force is acting in the opposite direction of motion, disturbance. Right? So this clarity must be there in your mind. So that's why we try to draw a similarity between mass spring damper system and angular motion dynamics of an airplane. Right? This was our understanding. And again, if you see here, when we are developing this dynamics, one-dimensional pitching dynamics, we also wrote equation of motion. And we use this concept m is equal to I into angular acceleration. This is angular acceleration, and which is typically we wrote as I double y into q dot. So that is the equation of motion, right? Okay. So if I correct, this is F equal to ma, and F was minus kx dot minus cx dot minus kx, sorry, cx dot. That was the force, right? And this was equal to m d square x by dt square for free response. If there is a forcing function, then we write ft minus this. So this is the equation of motion. Is a force balance. What are you using? You are using Newton's laws of motion. That means we are writing this equation both here and there with reference to inertial frame of reference. That is the catch point you must understand, right? And here there is a 1 degree freedom. Here it is also 1 degree freedom. It is angular, here it is linear. So this much we have understood. We have also understood how to transform equation from time domain to frequency domain by using Laplace transform. One advantage you get is once you take a Laplace transform, now those differential equation gets converted into algebraic equation, right? So this is just to revise whatever you have done last class. Why I stress again and again, please understand, we need to understand the basics, the foundation stone, foundation block before you go into the overall generalized approach. Otherwise, if these things are not clear in mind, it only looks like some mathematical operations you are doing without having a physical sense, and that will be too dangerous for a flight dynamics man to handle real life problems. Okay? Here also, please understand very clearly, we are talking about statically stable configuration. If the airplane is not statically stable, then the spring analogy will not work. Because spring analogy is, if there is a disturbance, you try to restore it. Imagine if this airplane was not statically stable, even if I give a small disturbance in alpha, it will not try to restore, it will diverge. So then this modeling will not be appropriate. So this is extremely important. When you are doing this, I am clear, when I am drawing this analogy, I am clear that I am talking about statically stable configuration. And for the statically stable configuration, you know dCm by d alpha should be less than 0. Right? That's the condition for static stability in longitudinal case. Right? Okay. Now think of, so far we are talking about motion like this or motion like this, pure pitching motion. But for an aircraft, it has more than 1 degree of freedom. For example, if I take aircraft, let's say this, and I fix axis system x, y, and z, and I call it body fixed axis system. That is, I write B, B, and B. So this XB, YB, ZB is the body fixed axis system. Let's say it is attached at center of gravity. And also we have aligned x-axis along the line of symmetry or along the chord line or along the fuselage difference line or along a line where the cross moment of inertia vanishes. So that is in our hand. The alignment of x-axis, x body fixed axis can be different for different types of purposes. Okay? So let's say in this case we are assuming that x is aligned along the fuselage reference line. Now, if I talk about degrees of freedom, you could easily see this body, which is an aircraft, it can have motion along x-axis, it can have motion, linear motion along y-axis, it can have linear motion about z-axis. So 3, 1, here, a linear 3, and also it could have rotation motion about each axis. So what will happen? This is roll, this is yawing, okay, and this pitching motion. So if I repeat it, if this is the aircraft, so it can have one motion like this, a motion like this, a motion like this. So along x, y, z, one could be rotation about y, pitching, rotation about z, yawing, and rotation about x, roll motion. So there are 3 translational and 3 rotational degrees of freedom, and that is why for a rigid airplane, we try to model it using 6 degrees of freedom motion. Okay? Please understand, I have written the word rigid airplane. That means throughout the analysis, the distance between 2 points on this airplane remain constant. So I can think of a not so rigid airplane if you think there is a high aeroelastic behavior of the airplane. It flexes, right? It's possible, right? For a highly maneuverable airplane, the airplane is not strictly very rigid. It could be aeroelastic in nature. But we are talking about rigid. And for that, we mean if you pick up any 2 points, their distance remain constant. Right? Okay. So we now need to develop equation of motion or equations of motion using this 6 degrees of freedom approach. That is, I need to develop equation of motion which should represent the motion along x, motion along y, motion along z, which is a linear motion, translation motion, and also rotation about x, rotation about y, rotation about z. Think of, in contrast, when you are talking about mass spring damper system, ideal mass spring damper system, we are only talking about rotation along x-axis, right? And here, it's a 6 degrees of freedom. This is one thing. Second thing, it is possible that there is a coupling between the motion along y and motion along x, or motion along y and motion along z. So it may not be possible for us to separately handle each axis motion. That coupling may come because of aerodynamics or because of inertia. Right? For example, you understand, if you remember, if this is the body and spinning about x-axis with a high RPM, right? If I give a disturbance like this, it will also precess like this. So there is a coupling because of inertia, right? So now the problem becomes a little more challenging, but not complicated, because all these things have been solved 50, 60, 70 years back. So nothing new we are doing, nothing rocket science we are doing. We are doing a very simple thing. Only thing, it will be simpler if you follow the steps in a neat and clean manner. Understand each step and go for the next. Learn through small perturbation. Don't jump. Don't assume anything without understanding. Okay? This is one difference. Second thing, also please understand, when we are doing this mass spring system, we are writing it x of t. So we are actually telling we are studying the motion along this axis, right? So it is extremely important to identify the axis. That is why you have seen here, we have denoted xb, yb, zb, and we have referred it to as body fixed axis system. But what is the problem? Why there is an additional thing we need to understand? Again, you come back here. Here also you have used F equal to ma or m d square x by dt square. That is, force equal to, force is the cause for acceleration, and Newton's law is mathematically put in this way, as long as you remember that mass is not changing, and also these are measured with respect to inertial frame. And that is why we say Newton's law is valid in its expression form F equal to ma when you are applying it in reference to inertial frame. If the frame is not inertial, you have to give some correction. That is to incorporate the frame acceleration. So let's not jump now. But one thing I understand, that I should do all the measurement with respect to inertial frame. So what is an inertial frame? That is, frame has no acceleration. Now see the problem. We are talking about aircraft, and we want to measure acceleration and then try to apply F equal to ma. And we need to measure this acceleration with respect to the inertial frame. But where is the inertial frame for an aircraft? Mostly for an aircraft which is a low altitude vehicle, we take Earth as inertial frame, although we know, strictly speaking, Earth is not an inertial frame because Earth is rotating, right? But for our analysis, especially for dynamic stability, since the duration of study is very small, we are talking about transient, we will neglect the Earth acceleration. We will also neglect the curvature effect of the Earth. We will take it as a flat Earth. And we will assume, for dynamic stability analysis for an aircraft, assuming Earth to be inertial frame is good enough. It will not cause much error. That is, one assumption we will be making. Once we make this assumption, then I can implement Newton's laws of motion in a frame which is fixed to earth. So I say x earth, y earth, and z earth. So now we have got two frame of reference. One is two frames. One is body fixed axis system, which is fixed to the body. That means when the body is rotating, this axis also will rotate. So definitely this is not an inertial frame. So we cannot directly apply F equal to ma in the rotating frame unless and until we give appropriate correction. And this is the inertial frame. If we write the equation with respect to the inertial frame, we need not give any correction. But you will find there is a demand to write the equation of motion and operate in body fixed axis system rather than inertial frame. What is the reason? The reason is, suppose this is the body fixed axis system, xb, yb, zb, and let us say this is x earth, y earth, and z earth. You could see I can keep on writing the equation of motion with respect to x earth, y earth, and z earth, and their earth fixed axis system, so inertial frame, no problem. But there are complexities. See, in actual practice, the airplane will have motion like this, right? Motion like yawing motion, rolling motion. And as we are referring to only earth fixed axis system, then you can understand the moment of inertia of the airplane, with respect to inertial frame will go on changing. That will almost become function of time, depending on the orientation. The moment of inertia will become function of orientation and time. That will create a lot of complexities. So we do not want to work directly in inertial frame. However, you cannot violate because Newton's law of motion is applicable only in inertial frame. This is one challenge. The second thing is that the aerodynamic forces they depend on the relative airspeed, okay, not on the relative ground speed. For example, airplane is there with respect to ground, it may be 0, but if there is a wind coming like this, it will experience aerodynamic force. So it is the relative airspeed of the airplane. So that is why it is advantageous to work in body frame. So that also makes work in body frame. Third, even if 1 and 2 you can manage, bigger question comes, how do I measure the orientation of the airplane? This is the airplane. If the body rotates, the axis also rotates. So how will I measure the orientation? Because with respect to the body axis, rotation is 0, because axis is also rotating. So there is a necessity that I measure the orientation of the body with respect to earth fixed inertial frame. So the orientation of the body will be measured with respect to inertial frame. And when you want to work in the body frame, you will see that total velocity of the airplane with respect to the inertial frame can be resolved locally into components along body x, body y, and body z direction. Similarly, also about the angular velocities. whatever angular velocity of this frame with respect to the inertial frame is there, that can easily be resolved along x, y, b and z, b axis. So, we will be using these concepts. But please understand, we need to work in inertial frame because we want to apply Newton's laws of motion, but operational wise we will like to find out a method so that we can work in a body frame without violating the fundamental law that Newton's law is valid in inertial frame. For that some correction will be. Okay.